Hey everybody, it's Mrs. Cassell. I wanted to actually follow through on the problem that we were working through in class today and give you a bit of a solution here. So I'll start the problem over from the beginning. So the idea here was that we've got a merry-go-round that's going around. We'll just go ahead and give it a counterclockwise direction since that's our positive direction for rotation usually. And then we have 4 people who all have the same mass who at some point in time jump on. So let's assume that they're spread out all around and they just go through. They're like on the north, south, east, west sides. So there's 4 people that go, ha! And they jump onto the merry-go-round. And our question really is, what happens to the speed of the merry-go-round, the angular speed of the merry-go-round, okay? So here we go. We'll think about a couple things that we know. So first, we know that an angular momentum is equal to a moment of inertia times an angular velocity. We know that the moment of inertia depends on the shape of the thing. So there's one thing that I said was missing from our notes because it literally is just like one piece of an equation. A point mass, the moment of inertia for that is mr squared. You'll see varying iterations of that where they write it with a capital M or a capital R, but that's the how we calculate the point mass of a person, okay? So what we'll think about right here is that some of the known values that are in our problem. So we've got our known values. We've got the angular velocity is given to us as, what is it, 0.8 radians per second. We know the diameter of our merry-go-round is 4.2 meters, so that means our radius is 2.1 meters. Let me make that look a little neater. We know the mass of the person, we've got 2.1 meters. The mass of each person, I believe, was 65 kilograms, and then there's 4 of those people, right? And we're given the initial, or the moment of inertia of the merry-go-round as 1,760 kilogram meters squared. Okay? I don't think there's anything else that's given to us in the problem. I think that's really it that we've got right here. So what we want to find, the thing that we're looking for, is we want to know what the angular velocity is after they jump onto the merry-go-round, right? So this is a collision, right? We've got an object in motion. We could consider the people like parked cars, basically. We've got a moving object running into a stationary object. In this case, we're using a little bit of magic, and the stationary object is running into the moving object. So one of the things that we know is that momentum is conserved in all collisions and explosions. So this is a collision, so we know that momentum is conserved. What that means for us is the initial angular momentum has to be equal to our final angular momentum. Alright, so when I take a look at that, what that means for us, our nice little equation that we've got here, we think about the moment of inertia before the collision. We've got that it's just the moment of inertia times the angular velocity. I'm going to write out the whole equation. We've got 2 sort of objects in the system here. We've got the moment of inertia of the merry-go-round times the initial angular velocity plus the moment of inertia of the people plus their initial angular velocity, which is 0, right? And afterwards, because they are now as one object, one system, it's the sum of their moments of inertia times their angular velocity final. Okay? I think my pen is dying. Okay. So that's what we've got for our equation here. So, next thing we've got is everything else in here, right? This becomes an algebra problem. I've got a moment of inertia times an initial angular momentum. I've got the sum of these. So if I want to solve for final angular velocity, I'm going to divide both sides by the sum of my moments of inertia. Cancels that out. So now I have my final angular velocity. It's going to be equal to the moment of inertia times the... Oh, let me pause this. Hold on. Sorry. Mr. Offer came in here. Okay, so we've got our moment of inertia of the merry-go-round times that initial angular velocity divided by the sum of the moments of inertia. So now we've got numbers that we can plug in here to solve this problem, all right? So we are told that our initial moment of inertia is 1,760 kilogram meters squared times our angular velocity, which is 0.8 radians per second. Well, that's all divided by the sum of these moments of inertia. So the moment of inertia of the merry-go-round, yep, we're using the same number twice. Do not despair. Trust your math. That makes sense, okay? So our initial moment, or our moment of inertia is 1,760 for the merry-go-round. And for the people, we have to think through, and we are going to use this equation that's up here at the top. So I think I'll actually do that work up here for the people. So the mass of each person was 65 kilograms. They are hopping on at the radius of the merry-go-round. So they're at the edge. So this radius is going to be the 2.1 meters, and that's going to be squared, right? So I need a calculator. Here we go. 65 times 2.1 times 2.1. So this says that the moment of inertia for one person is 286.65 kilogram meters squared. Okay, sorry, that super washed out my camera. So this number right here, okay, there are 4 of those people. So I'm going to need to multiply that number times 4. 4 of those people, here's my number, times 4. 1,146.6 kilogram meters squared. So there's my number. I'm going to put down here at the bottom, 1,146.6 kilogram meters squared. Now, I just have another calculator problem. So I'm going to go ahead and do that without 1,676 plus 1146.6 equals. So that's 2906.6. Alright, I got 1,760 times 0.8 divided by 2,906.6 equals. So my final angular speed for my roller coaster, or angular velocity, I'm being specific here, is 0.484 meters, not meters per second, radians per second. That's how much that is. So not quite half of the initial angular velocity. Right? So the second part of this question actually asks sort of the opposite. It says, what happens if these people jump off again? So here's where you could bring in a little bit more physics understanding, sort of to answer part B of this problem. If we want to think about what happens when they jump off, right, we have to think about that they're exerting a force to do so. So we want to know, does that force cause a torque? So if this is the edge of the merry-go-round, okay, so here's my radius is over here, right, and the person jumps off. They jump off radially. They jump off that way. That's the direction. So they're exerting a force along the radius of the merry-go-round, okay? So that's the force of their jump. So let's think about if this is my radius and I want to measure the angle between these, right? Here's my radius. There's my force is pointing in this direction. This angle right here is 180 degrees. Or if you drew it differently, it's 0. Either way, think about the sine of 180 degrees is 0. So these people, if they jump off radially, so they literally jump off with, like the center of the merry-go-round at their back, and they just go, and they jump straight off so that they are still in line with the radius when they do, rather than like jumping where they're pushing sideways or something like that. If they just jump straight off, they don't exert a torque on the merry-go-round. So that's one of the tricky things to think about. So here's the crazy thing that happens. If there's no torque, then there was no external force applied to the merry-go-round. So this now is just an explosion. It's this problem in reverse. Here was the angular velocity. Now we need to solve for the initial angular velocity, but there's no other forces, there's no non-conservative forces in here. So this momentum stays conserved, which means if we work through this problem literally backwards, we get back up to our same initial velocity. So if these people jump off the merry-go-round, it resumes its initial angular velocity of 0.8 radians per second. So there you go, everybody. There's the answer to the problem we started in class today.